Hello everyone. Bonjour à tout le monde. Spot is on, the Science Public Online Talk series brought to you by the Faculty of Science at the University of Manitoba. My name is Samar Safi Har, Faculty of Science Lead for Equity, Diversity, and Community. On behalf of the faculty, I welcome all of our viewers joining us online today. Today's talk is by Dr. Susan Cooper, joining us from the Department of Mathematics at the University of Manitoba. Before we start, I'd like to acknowledge first that the University of Manitoba campuses are located on original lands of Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories, we acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. Thanks to support from the Faculty of Science as well as of all of our invited speakers, this series was created to support all of our students, engage and connect with our community, and hopefully reach out to everyone through science during these unprecedented times. Science knows of no borders. Science is enriched by our diversity. In light of all of the crises happening around us, the pandemic, bias, and racism that continue to harm segments all across society, especially the vulnerable, underprivileged, we hope that science helps us cross these boundaries, support each other, and stand in solidarity to support those hurting. In order to reflect and pay respect to those being oppressed, I would like us all to pause with a brief moment of silence. Thank you. Now to the talks. So these are meant to be brief, 20 minutes long, so please stick with us till the end. The question and answer period will be likewise about 20 minutes long. And to enter your question, please go to slido.com and enter the event code K873. Feel free to enter your questions throughout the talk. I'll be moderating and reading out the question. You can enter your name if you choose to or choose to remain anonymous. If you have any questions or face any difficulties, please send an email to andrewpapil@humanitoba.ca. Now it's my great pleasure to introduce today's speaker. Dr. Susan Cooper is an associate professor in the Department of Mathematics at the U of M. She completed her undergrad at the University of Regina and received her master's and PhD from Queen's University. She's passionate about sharing the joy and beauty of mathematics, a discipline that's at the root of sciences. Her research area explores the intersection of algebraic geometry and commutative algebra. Susan describes herself as a BROG, B-R-O-G, type mathematician. That term is a hybrid between a bird and a frog. And where did that come from? Apparently, theoretical physicist Freeman Dyson once categorized mathematicians as being roughly two types, birds and frogs. The bird is the big picture type mathematician who flies over the mathematical landscape looking for ways to link concepts from different areas, whereas the frog is the more detail oriented mathematician who worries about the details of specific problems, aiming to find a solution to each. So, as a hybrid, I guess Susan is both. And her talk will be about the strength of a secret. Dr. Cooper, welcome. Over to you.
Well, thank you very much to everyone who decided to join us on a Friday afternoon. And thank you to the Faculty of Science for organizing this lecture series and for the invitation to talk today. As mentioned in the introduction, I am a mathematician and I study algebraic
Susan, it looks like we lost you because we can't hear you. So we are still live. We're going to try to find out what the problem is from Susan's end. So please stay with us and we'll get back to you. Thank you, everyone, for your patience. We're still trying to reach out to Susan. Not sure what happened, but we'll be right back.
Okay, I have a message here that I'm good to go to start over. So I am going to do that. I apologize for the technical difficulties, not sure exactly what happened. But let's see what we can do to pick up. So as mentioned in the introduction, I am a mathematician and I work in the area of algebra. And in doing so, I handle a lot of abstraction. So I would like to emphasize 3 points in this presentation. First, I would like us to realize that abstraction allows us to solve real-life problems. Second, that abstraction allows us to study problems using different approaches. And finally, that abstraction can be beautiful in its own right. Now, the application that we want to use today to motivate the talk for the real-life problem has to deal with coding theory. And coding theory deals with the study of properties of codes, which many of you will think of as sending and receiving secret messages. There are lots of reasons for why people would invest a lot of time, energy, and money into such study. One such reason is national security. Certainly, countries would want to talk to their allies in confidential and secure and safe fashions. And the second one, just to name a few, would come from, well, you, the audience. So I'm going to bet that at least one person in the audience has purchased something today with their credit card online. And we would want banking institutions and businesses and our computers to be able to deal with that confidential credit card information that we have so that we can feel safe and secure in how we're conducting businesses. Another example where we might be interested in studying coding would be two-way communication between two friends, or in this case for this talk, two brontosauruses at the suggestion of my 5-year-old son. So what we're going to have is we're going to have brontosaurus number 1 and brontosaurus number 2, and they're going to be having a conversation while eating some tasty leaves because they're herbivores. And they would not be overly thrilled if there was an introduction of a predator who could intercept their communication. So in this talk, we're going to have a T-Rex for our predator. Full disclosure that my 5-year-old also recently told me that brontosauruses and T-Rexes didn't live at the same time. So my apologies for the dinosaur enthusiasts. But what we want to talk about is how the two brontosauruses could set up an example of what we call a linear code in mathematics. So before they even get started in their communication, what they have to do is decide on a translation key. So they're going to choose, in this example that we're going to use, 26 letters from the English alphabet and 3 punctuation marks. To each letter and punctuation mark, they have to assign a number. So there's 29 symbols in their alphabet. So we are going to go ahead and we're going to assign A to the number 1, B to the number 2, and so on and so forth. We'll get down to 28, but it is typically, for mathematical reasons, handy to have a 0. So the exclamation point is going to be assigned 0. So we have 29 numbers there. So that's how they're going to translate their alphabet. And then once they translate it to a number, they're going to want to encode that number. The way that they've decided to encode it is to multiply the number by 3. Now you have to be a little careful here because we have numbers in our translation chart, such as 26, such that when I multiply 26 by 3, I get a number that's not seen in the chart. It's too big. It's bigger than 28. So what do we do in that case? Well, we have to use what we call modular arithmetic in math. So for the letter A, we're going to assign it the number 1, and then we're going to add to it 29. This is because we have 29 numbers in that previous chart. We'll get 30. Add another 29, and you're going to get 59, and so on and so forth. So any number that can be written as 1 plus a multiple of 29, what we're going to do is we're just going to treat it as if it is the number 1. We'll do that for B as well. B was assigned the number 2. Add 29, you get 31. Add another 29, you get 60. So any number that can be written as 2 plus a multiple of 29 is going to be treated as if it's just the number 2. And you're going to do that for the entire alphabet in your setup. Okay, so that's how we're going to encode by 3. Let's look at an example. Let's suppose that brontosaurus number 1 has had a lot of leaves to eat. And so he's going to want to send the word water. To do so, he translates his W to a corresponding number. W is the 23rd number in the alphabet. And then he multiplies 23 by the number 3 to encode it. There you get the number 69, which can be written as 11 plus a multiple of 29. So we treat that output 69 as the number 11. So W is translated to 23 and then encoded to the number 11, which you can see down below in our chart. And you would do this for each letter in water with an exclamation point. So here I've done the work for A. A was the first number multiplied by 3, and it gets encoded into the number 3, and so on and so forth. Well, one of my goals was to emphasize that we can look at things in different ways in mathematics, and doing so, we can look at the analysis of a problem with richer information. So here we take water, we translate it to this string of 6 numbers, and then we encode it by multiplying by 3. We're going to use fancy math notation and call this output vector or output sequence a vector. So 11, 3, 2, 15, 25, and 0. Well, how did we get the 11? The 11 came from looking at 23 and multiplying it by 3. How did we get the 3? We had the number 1, and we multiplied that by 3. So you do this for each entry in that vector. Well, there's another way to rewrite that. I'm going to take this vector, and I'm going to kind of decompose it and pull it apart. So if you focus on just the red part, the 3 times 23, I'm going to pull out the 23, and then I'm going to record that I had multiplied it by 3, but since I want to pull this apart, I'm going to keep all the other 5 entries of my vector as placeholders by putting zeros. Then I'm going to move over to the 3 times 1. Pull out the 1, and notice that this is in the second component of a vector, and multiplied it by 3, zeros for placeholders everywhere else. And you do this for every possible digit or number in the set vector of 6 entries. Well, we can write that more compactly by taking out the numbers that we pulled out, making them a vector, and then the vectors that we have with just 3 in one spot and zeros everywhere else, we make them the rows of an array, and we call this array a matrix. Okay, so what's important to note with this viewpoint is that our coded word is just linear combinations or combinations of the rows of this matrix. So we're focusing on the rows of this array. There's nothing overly special about the message water. I could have taken any 6 entries, and I could have written it as that 6 entries in my vector and linear combinations or multiplication of this array. This array is called the generating matrix, and it's really controlling how we find our coded messages. That is an example of a linear code. A code word, that's all of your outputs, is going to be any non-zero linear combination of the rows, just like we had on the previous slide. So let's see what we can do with that T-Rex. Let's suppose that T-Rex introduces an error. He's going to intercept Brontosaurus number 1's message, and he's going to send the encoding for Wasser. So in water, he changes the T to an S. And our question is, can Brontosaurus number 2 decide if this is what Brontosaurus number 1 intended to send? Another question that we could ask is, can we measure the distance or the difference between Wasser and the nearest English word? And so to look at these problems in a mathematical way, we introduce a number, which we're going to call D, and its formal name is called the minimum Hamming distance of our linear code. And what it does is it gives us a lower bound on the distance. The larger the number is, the stronger our code is, because we have more room or distance to decide the difference between what was sent and any error that might have occurred. So we'll come back to our water example with the dinosaurs, and we'll look at the definition precisely. The minimum Hamming distance is the minimum norm of a code word. These are just vectors, x, which are non-zero. Well, what is the norm of our vector x? It's simply the number of coordinates in our vector, which is not 0. So coming back to our example, Brontosaurus number 2 received the vector 11, 3, 2, 15, 25, and 0. There were 6 entries in that vector. 5 of them are non-zero, and so the norm of that vector is 5. But remember that our minimum Hamming distance is determined also by looking at the rows of our generating matrix. In particular, if a code word is any linear combination of the rows, then a row by itself is considered a code word. So if you look at any one of the rows in this generating matrix, we have only one non-zero entry. And so indeed, for this example, our minimum Hamming distance is the smallest of these norms, which is 1. Okay, so that's but looking at the problem of linear codes by looking at the rows. But what we want to do now is we want to change our lens, the viewpoint that we're looking at this. And we're going to look at this by now changing to focusing on the columns. So suppose we have a linear code, and I've written down its generating matrix here. What you'll notice is that I've color-coded this. The columns in red are all the same. And then I've got the next two columns in black. They're equal to each other, and the columns in green as well. It turns out that if you look at the columns, those entries are coordinates for points in a weird geometric land. I call it weird because many of you may not have been exposed to it yet. We'll talk about that in a moment. But the number of times that you see the columns, that is going to be your multiplicity of that point, or the multiplicity of that column. So our question now is, or our approach is, can we bound the minimum Hamming distance of a linear code using algebraic and geometric properties arising from points in this new geometric land? And the new geometric land is called projective space. So to understand what projective space is, what you do is you look at your Euclidean plane. And if you haven't heard of those words yet before, what you're going to do is you're going to picture yourself standing in the field of the prairies of Manitoba. And anywhere on that ground, you can see infinitely in any direction, but you do stick on the flat ground. That is your Euclidean plane. And in that Euclidean plane, if you were to draw two lines, they're either going to cross each other or they're not going to cross each other. They're going to be what we call parallel. So historically, what happened is we wanted to make that a simpler situation. So what we did is we added points to that plane, and we added them in such a way that we added points to the lines, and we declared that if the two lines never did cross each other, well, they do in this new geometric land, and they cross at a point called at infinity. So projective space is a fantastic geometric land because it's kind of what you see is what you get. And so now if you stand at the back of railway tracks, what you're going to see, even though we know that they never cross, is it looks like they are now going to cross. So I'd like to close by just giving you an idea of what can happen in this new perspective. So if you focus on the code, linear code here with generating matrix, notice that I don't have any repeating columns. And so I have what I call a simple set of points. And just forget about that last row of ones. That's a formality for projective space if you don't already know it. But if you look at the first three columns, you'll see some numbers in purple. 0, 0 is a point in Euclidean space. 1, 0 is a point in Euclidean space. And 2, 0 is a point in Euclidean space. And we have a way of kind of plotting coordinates for those points. And if you do that, you're going to get that they all lie on a line. And I've color-coded that with purple. They lie on a horizontal line, H1. And similarly, your last three columns, those are going to give you points that are colored black in this case. And they're going to happen to lie on another horizontal line, H2. And so a result of Tovenu and Van Tuyl says that if you look at the minimum Hamming distance for the code with this generating matrix, it's bounded by taking the number of horizontal lines, -1, times the number of vertical lines. Whenever you are able to do this, and you get a grid-like formation, a box, if you will. Okay. And so what was important in improving this result? Well, it turns out if you take the product of these two horizontal lines, let that be F, and the product of these vertical lines, let that be G, then those are two polynomials, and those two polynomials have no common factor. So by switching our viewpoint to columns and using algebraic and geometric information, we're able to classify or bound the minimum Hamming distance of a family of linear codes. Now, what I'm going to do in the next slide is I'm going to take the exact same set of points, and I'm going to repeat the columns for all of the columns but one. So I'm going to add multiplicity. So I've taken away the labeling of the pictures there, but you can see that the first two columns are the same, the next two columns are the same, and so on and so forth, but not that last column. It's different. So I've added a bit of fattening or multiplicity to the points, except for that skinny one there in the corner. I still have my horizontal and vertical lines. And in this case, Tovano and Van Tuyl conjectured that we can yet again bound the minimum Hamming distance. How do we do it here? Well, I repeated each column twice. So that's my purple multiplicity 2. I'm going to take that 2, multiply it by the number of rows, add to that the number of vertical lines that I have, subtract the multiplicity again, and then subtract off 2. Then I get a further bound here. And indeed, this is going to be true in general whenever I have multiplicities added in such a way. And for our last example, I'm going to look at something that's a little different. I'm going to look at what I call a star configuration. So this star configuration has a very large generating matrix for its associated code. But what you want to pay attention to is that I've got 5 lines. And how do I get my points? I take the intersection of any 2 lines. Then what I do is to each line, I'm going to add a multiplicity. And the multiplicity has to be 2 times something. So in this case, it's 2 times 1 everywhere, except for 1 point. It gets something special for a multiplicity. It's 2 times something plus a number. Okay? And those multiplicities, remember, in your generating code for your the generating matrix for your code, these multiplicities are telling you the number of times you have these columns repeated. So this is a very large matrix. And in this case, Tovano and Van Tuyl were able to conjecture a bound on the minimum Hamming distance. And a student who visited me last year from Lyon, Emilien Zabeth, he and I showed that you can achieve this conjectured bound. What you do is you take 1, which is 2 times the 1 for most of the multiplicities, and you times it by the 5 lines minus 1, 5 lines minus 2. That's going to give you an exact equality on that minimum Hamming distance. And then you have this bound, which is also color-coded. So in summary, what have we done? We've looked abstractly at a real-life problem. And the real-life problem was looking at the minimum Hamming distance of linear codes. How strong was the code? The larger that minimum Hamming distance, the better your code. And we were able to use different viewpoints. We started by looking at the rows of our generating matrix, and then we switched the viewpoint to looking at columns and how many times a column appeared in order to get bounds on that minimum Hamming distance. So it was the different viewpoints which allowed us to look at this and have a better analysis. And indeed, we got beautiful results by just doing that. Thank you.
Thank you very much, Susan. And thank you for sticking to your time despite all the technical difficulties that we faced. I hope everybody's still with us. So please enter your questions on slido.com, event code K873. And so maybe while waiting for the questions to come in, Susan, I'm curious for the youngsters that are listening to you and they are fascinated by mathematics, maybe you could tell them, how did you get into this? And, what do you see that excites you the most about applications of what you're doing to the real world?
So it's a kind of a funny story how I got into mathematics, actually. I have an older sister who is a biologist, and she's working in California. And she named me, actually. She gave me my name, and I think, well, she's going to kill me for saying this, but I think that she kind of took that as she got to control me. So I went through a lot of different majors as an undergraduate. One of them was performance theater, and I was very artsy. And then my sister pretty much told me she wouldn't talk to me again unless I didn't try mathematics. And so I tried mathematics, and indeed, I just really enjoyed the ability to think through things, and I had a very good, lovely support group at the time, and so I think that made a huge difference. But I am a pure mathematician by training, and so the algebra and the geometry that I do is typically very abstract, and so the coding theory is probably one of the better, more concrete applications that I have, and I'm certainly trying to branch out a little more. But there's a group of us who are also trying to look at something called Hadamard products, which has applications in statistics and physics. So I think it's one of those disciplines where you really have to allow yourself to branch out and learn lots of new things to do the real world applications.
Okay, thank you. A question coming from Sobi. Online communication is sometimes hacked successfully despite supposedly safe encryption methods. Is that because of the weakness of the encoding or by luck?
I'm having troubles reading the questions. I don't know if we can make them larger for me, or you can repeat the question.
Yeah. So I'll repeat. Online communication is sometimes hacked successfully despite supposedly safe encryption methods. Is that because of the weakness of the encoding, or is it by luck?
I would say it's both. Certainly, the more work you've put into making it a secure encryption system is helpful. But with many things in life, including research, sometimes you luck out. I guess it's unlucky if it's your code, but if it has been hacked, I guess that you're potentially feeling lucky. But some people are lucky, and some people are very good at guessing patterns from other people. So I would say it's a mixture of both.
Okay, thank you. A question from Adam KS. Is it easy to guess the code used by a bank or credit card company?
I hope not. So I actually don't know the answer precisely to that. I would hope not, right? They're probably spending, in fact, they are spending significant amounts of money making sure that their codes are not able to be hacked. That said, the day we went under lockdown for COVID, my own credit card was hacked, and somebody bought a lot of Starbucks off of my credit card. So, I mean, it does happen, but they have a very invested interest in making sure that they've done their best so that it doesn't happen.
Okay. Question. I hope I understood the use of matrices properly. Since one could use a matrix for generating the code of a given vector, are inverses of those matrices required as the other end would need to decrypt it?
Is it required? Certainly handy to have. So linear codes are not the most complex codes to be looking at, but if you start getting into things like RSA encryption and what like, you're going to have to undo what you've done to encrypt the code, and so that is the idea of the inverse. Yes.
Okay. A question from Laplace transform. Took your abstract linear algebra course 1.5 years ago. I'm wondering, is linear algebra related to functional analysis?
Well, in my opinion, linear algebra is related to pretty much everything. I didn't actually, as a student, I did not like linear algebra. I'm going to be honest. In fact, it made me change majors for a little while out of mathematics. And I realized after some time that every time I tried to go back into mathematics, I was having to deal with ideas from linear algebra. I think it's one of the most critical and crucial courses you can take, even though you may not see the beauty of it right away. And so, yeah, there's relationships there.
Okay, another question. Is there any different approach other than matrix theory to this problem?
So if you mean the problem of linear codes, I mean, the idea was matrix theory. So so if you look at the talk again, so near the end, you'll notice that we were using the points in projective space and their multiplicities. So if you deep down, and I didn't go into the details because there's not enough time to go into those details in a public lecture, but if you go deep down into that, we're not necessarily focused on the matrix itself, but we're looking at the properties of the points, and they're very geometric and algebraic.
All right. Next question. Does your work include dealing with protecting against the code cracking that quantum computing hopes to eventually decrypt? How might it apply to this field?
So my personal work does not, unfortunately, deal with that. So I can't. It's a great question, but I don't think I can handle it with the to the level that you're looking for. Mine is just so my approach is really, or my intention is to just get these bounds on the Hamming distance, and I leave the quantum to the quantum experts.
All right, so that's it for the questions. Thank you everyone for your great questions. And thank you very much, Susan, for being with us today and sharing your work with us. So I guess the next thing I'd like to say is what's coming up next. So if we can switch to my screen. Thank you. So yeah, I just wanted to make sure to thank again the Faculty of Science and the support team for the SPOT series for their hard work bringing this together. And of course, all of our speakers, including Susan, who are without whom this would not have been possible, and for helping us make this accessible to everyone around the world. Our next speaker, who may be familiar to many people, is Dr. Jim Peebles, the 2019 Nobel laureate in physics, and originally from Winnipeg. So he's going to talk to us next Friday on the lessons on the nature of physical science from the study of the expanding universe. So I hope to see you all and more. Please pass the word to your friends, colleagues, and everyone who would be interested. I'd like to remind everyone that these talks will be available for later viewing. They are posted on the Faculty of Science YouTube channel, so feel free to watch anything you have missed or you might miss in the future. So thank you, everyone. Have a great weekend and hope to see you next Friday. Bye for now. Bye, Susan.